Hello and welcome to this video on the Imperium's final solution to unsolvable Xenos, heretics, mutants and fairies, the Life Eater virus. The Life Eater virus is a weapon delivered to a platform, vessel, planet or any other relatively limited space via a remote delivery vehicle. For example, Orbit to Earth missile. It's used to enact the final and ultimate judgment, Exterminatus. Exterminatus is generally only undertaken in those extreme circumstances where a potential or actual extinction level threat to the Empire exists, and the planet, poses a threat to other planets and Imperial worlds, such as when the fairy con is announced in a given city. We have several examples from Warhammer of the Life Eater virus either being used, set up to work in an emergency, or at least a broad description of what does happen when used and to some extent how. This is both great and terrible. The choice to push the metaphorical button quite literally embodies Oppenheimer's quote, "I have become the destroyer of worlds." The process to do so begins when the virus is rather obviously released. Whether it's a small virus in a vial on a black ship, a deliberate delivery to destroy heretics, or a failed launch such as on Armageddon. All of these begin the process of releasing the Life Eater virus and the consequential Exterminatus. The description of this is relatively straightforward in what it contains. Once it is released, it becomes aerosolized. This is generally done using virus bombs. It is supposed to be extraordinarily virulent and capable of infecting every living thing, whether it's flora, fauna, microscopic organisms, anything is free game to this. And within minutes, it will cover the entirety of a planet, so long as 100% orbital dispersal is achieved, and that's generally considered a given. The pathogen itself can even penetrate sealed environments. That is, only the exterior hull of a ship will be safe from it, and even entirely contained safe suits, such as Astartes armor, will not be able to resist it. The virus is designed to cause all the cells of whatever its host is to begin lysing. This effectively melts the host into, something rather unpleasant and rather reminiscent of high school lunches. This means anything and everything that is living, whether it's a forest, a massive mushroom colony, an ant colony, microscopic organisms in the ocean, schools of fish, anything will be dead. And this will happen in a very short period of time. But that short period of time will feel like eternity to the individuals and organisms involved, as their death is excruciating. This relatively quick and very painful death does result in the release of great volumes of flammable natural gases. Now this is supposed to be mainly methane, which will make more sense later in the video. As infection spreads across the world and you get an ever-increasing amount of natural gas being generated, you end up with a very combustible environment, and it requires almost nothing to begin the fiery hell that will destroy the world in the end. And that's simply something like a lightning strike, a static building up, or a deliberate ignition event. This leads to a, planetary firestorm, and whether you've died from the virus, you die from the lack of oxygen from the fire burning, or you died from the heat, it's rather irrelevant. But what happens to the planet after this is that everything is gone. It is burnt to cinders. And not the kind of cinders where you can get it going again with the additional process of a very difficult FromSoft game. All of this information is both very helpful and kind of contradictory. That makes it easy to begin to understand the Life Eater virus, but getting beyond the superficial is going to be rather difficult. This is a problem not just due to the Mage's biologist's phobia of new technology and perception of exploring known technology as heresy. Rather, the actual biology and, to a certain extent, science involved is much more difficult. Based on what we do know, we can break down the virus into several streams or areas that tell us a lot about it. These being the delivery, storage and various platforms involved, the wide range of hosts, the infection and spread rate, the activity, and finally the products made. These 5 areas can help and, to a certain extent, hinder our understanding, with some definite contradictions already known, and some very counterproductive behaviors. First, we have the platform, delivery and storage. We know that the Life Eater virus needs to be cared for, at least for some time. We also know that it has a definite need for care, as the example in Armageddon shows us that with care and maintenance, and more accurately without care and maintenance, the missile silos with life-eater virus warheads not only failed mechanically, but also biologically as a weapon. That means the weapons last less than 500 years, but more than a few years. That's because the black vessels have a vial of this bioweapon on board, and they can take decades or even centuries to travel between worlds and then returning to Terra to collect their kindling for the Astronomicon. This creates a rough period of between 200 and 300 years where we can estimate the virus might survive up to, with, well, little to no support, let's say. Obviously with more support at the start, and to a certain extent with effort at the end, you might be able to revive it. But that's the area that we need to worry about, roughly 200 to 300 years, where the virus will manage. That also brings us to comparisons to our real-world viruses. For example, the longest living virus in our reality is the norovirus, and for example, this can live up to several weeks outside of any host. This is very obviously nowhere near enough time. It's in fact many centuries short. That does bring us to how we could make it survive for long enough and trigger activity when needed. First, we have survival. This can be done with a relatively simple solution, the cell culture. Whether microbes such as bacteria, mammalian cells such as those used in molecular biology, or some sort of host organism, such as fungi, plants, or even small animals like tardigrades. These would all individually, and to a certain extent collectively as a combination, act as a longer-term viral host. That is, keeping it alive, especially if it is seemingly close to frozen, but not absolutely frozen. This would be better if done with tardigrades, for instance, where they can survive being frozen, and as a result, if the host survives, it's very likely the virus would survive, and this can be kept going for several centuries, but we're not sure of this, but it's the best answer so far. Of course, you would then need to effectively defrost the virus warhead shortly before deployment, but we'll get to that in due course. This does bring us to the issue of platforms. The virus is supposed to be stored in vials, aerosolized across worlds, and any other method that the Inquisition or High Lords consider necessary. That does mean we need a format or platform that is liquid, can be aerosolized, and arguably verging on a gas that can be spread very easily. We do have some real-world examples to draw on, controversial examples, but solid anyway. The terror attacks in Japan, wherein terrorists from the Orm-Shurinko cult tried to release and infect Tokyo train commuters with sarin. While the attack was a relative failure, it did kill 13 and severely injure 50. Not quite the life-eater virus target goals, but the level of danger or harm was still significant. Where the cultists failed was that they did not have delivery down right. As with the life-eater virus, it needs to be deployed in a way that it dissipates readily. This is done by using both an emulsifier to make the virus mixture miscible, and a solvent to make it easily break up and spread. For a single black ship and controlled deployment, such as through vents in air systems, this can be done by mixing with air and more solvent to make it spread. It would be like adding sleeping gas from Hollywood films and security systems. You're also not having to worry about a lethal dose, as you want a lethal dose. Therefore, that's relatively straightforward. On a planetary level, things get harder. The USA gives us some guidance. Well, it gives us a lot of guidance in many things, but in this case, we're talking about the gay bomb, not a slur or party name, but a real research project. They wanted to turn enemy combatants gay, and they would be so busy staring at each other's arse and thinking, "Oh my," that the US Army just could roll over the position with little to no combat. While incredibly ambitious and hilariously wrong, it does tell us about disseminating a bioweapon a very large area. This in conjunction with weapons research on things like Agent Orange and other less palatable examples, we can see how hard it is to spread an agent in atmospheric conditions. Using Earth as an example, we must cover 510,064,472 square kilometers, or about 316 million square miles. And to get just 1 gram, or about 1/30th of an ounce of virus across Earth, that is roughly 1 gram per every kilometer, with a roughly 75 to 25 ratio of solvent to virus in the warhead, we need approximately 81,610,315 litres, or approximately 21,559,000 gallons of virus. A SpaceX Falcon 9 rocket carries approximately 346,801 litres of liquid oxygen fuel. The virus warhead needs to be 235 times bigger than this to destroy Earth. This would also be why the Armageddon example used had multiple silos and launches to achieve the coverage, or lack thereof. Even then, we have a problem, and it's not an insignificant problem. You cannot compress this either. That is because compression will either kill the virus, the host, or both. So no compression means there's no practical way to make it a smaller payload. This also brings us to the platform. We've covered the storage and delivery, but how do you keep it ready to deploy, and how do you get it to a point where it can be deployed? Simply put, rockets. Rockets are good, as the friction and shaking of the launch will mix your virus and solvent, so no need for other agitation. It will also remove any sedimentation or similar. The process of launching can also be used to generate a small amount of heat that can be redirected towards where your payload is, both from friction of the rocket being launched and from the rocket launch itself, and this ensures that your previously near frozen, if not frozen, sample becomes not frozen and therefore ready for deployment. Next is of course the subsystem. You'll need multiple sub-launches. Think of a warhead that breaks away into multiple smaller warheads. This will be needed to spread your life-eater virus across the world. You can't just rely on near-orbital deployment to cover the entire planet. You would be lucky to get half the world, if you can get it to survive at all. Not just do you have the issue of it burning up on re-entry, but it's really cold up that high, and you might well kill the hosts and/or virus. So multiple subsystems that launch once it reaches near-orbital height is necessary. This will also ensure that your virus remains alive as it's being heated. This will get as high as possible, such as near to space, or more likely comparable to an ICBM, at about 1,200 kilometers or 750 miles high. Here it breaks into its subsystem and sends the smaller rocket payloads off in all directions, and the core system begins falling back to Earth. Ideally, the other rockets will travel fast enough by the time the primary rocket begins falling back to Earth and reaches a height of about 25 kilometers or 15 miles, they'll all detonate at roughly the same time and level. The fallout from this virus will cover an area of roughly 10,000 kilometers square. This would also require a ridiculous number of sub-munitions, at about 51,000, but let's keep this simple and assume one big rocket. That covers your world with, and in this case Earth, with the life-eater virus. But now we've released the virus, we need to look at the target host. Or maybe it's more accurate to say just life in general. This is the rub of the life-eater virus. It supposedly infects every living cell of every plant, animal, bacteria, fungi, and anything else you might think of. This is a problem. Just think how realistic it is to be able to use any tool in the world. Anything from a wrench to a highly specialized and unique item with practically no users alive today. That is the sort of thing the life-eater virus does, and why it is a problem. No virus alive today can use any and every possible host. They just don't work that way. It is why bird flu is only just able to spread to cows and humans, and even then it does not spread further. It's taken a lot of time for it to mutate to be able to do that, and it's not able to jump, for example, from cows to humans necessarily, nor can it necessarily jump from cows to pigs. Different species, different ways of accessing them. Generally speaking, this owes to the receptors or the signals the virus must use to enter a host. Because of this, the life-eater virus must have some sort of universal passkey, a multipass if you will. It's possible that the virus is using a very ubiquitous receptor or similar. The GTP binding proteins are an example. These are an incredibly common form of transmembrane receptors. That is, they are very common, rather large, and not necessarily easy to hijack, but possible. It might also be that the signal the virus is using is flexible enough to fit multiple receptors by altering its conformation on the go through isoelectric point. That is, a protein matches to the receptor because it can fit into the broad shape, and then this vast area around it causes it to shift and fit the lock, even though it shouldn't. Something like a bump key. The final option is the possibility of a giant genome. That is a genome with many redundant genes for many different receptors that may or may not be needed. Basically a scattershot approach of if there are enough ligands and the virus is able to find something that'll work eventually, it'll all pan out. An approach like Tinder pickup lines, where if you say hi enough, someone with daddy issues will respond. An impossible barrier, if there is just one virus in life overall. This does leave us with a last option, but this drifts away from the life eater virus to the life eater virus as simply a general term for a combination of very closely related viruses, but with very different target species. This would be useful as it would allow for the virus to collectively target all species, and not need to be able to infect every species with just one virus. If you have commonalities, such as sharing a host, so for example, they can all access tardigrades through the same common receptor, then you can have a bunch of different other receptors that are also usable by different, let's say, clades or variations on that same virus. And so you can keep them alive, but once released, a preferred host is available, and they can infect it preferentially. With so many species being viable, if not intended hosts, we have another issue. How do you infect them all and spread? Well, we've touched on the possibility that you could be using receptors, but we also need to look at not only the infection, but the spread once that host is infected. After all, if your virus doesn't find a host, it can't do its job. But if you only infect one host and there are 99 others that don't get infected as a result, you've failed your job. And the Inquisition will likely want to have words with you. The life eater virus supposedly starts to practically melt the inside of a host after all, and doing that to someone is probably not going to put you in the good books. While we're also reenacting the Raiders of the Lost Ark opening scene, it can be fun and all, but isn't exactly conducive to a virus surviving for very long, let alone infecting more hosts. The breakdown process is straightforward in a way. A virus will eventually destroy a host cell if the virus is pathogenic and virile enough to spread, and hijack the cell's machinery. We've effectively covered the virility element of this already. This is one reason why things like Spanish flu and Ebola don't last very long, and we can compare these to the life eater virus. Certainly they don't last very long in general terms at least. Using the Spanish flu as an example, it was very lethal, as it did just what we wanted, but the host died before they could infect a new host. Ebola is similar. It is deadly enough that people die from it before spreading it. The life eater virus needs to follow a very delicate balancing act. The process has to be more akin to what would happen in Plague Inc. That is, laying low and waiting while the world is infected and then suddenly flipping a switch and becoming lethal. This also won't really work, unfortunately, because it doesn't match the lore or fluff. Remembering, the life eater virus is able to kill very quickly. So how do we balance lethality of killing very quickly and painfully, while also lasting long enough to spread? The first answer is that it is deadly. That is, it burns through cells very quickly. However, if it starts with certain fast-dividing cells, such as the liver, enteric epithelium, and even your integumentary or skin-based epithelium, it would use fast-dividing cells first. Now, these would replace the virus-infected cells that are being destroyed, and in doing so, it would prolong the host's life in a manner of speaking. The degree of suffering makes the word life perhaps overly optimistic, but they're not dead yet, so moving on. As these cells are used up and begin to run out, it would then use the next and most readily available cells. This would both lead to the virus-using cells going from the GI tract out and skin in, a sandwich approach. An approach that keeps the host alive, but in increasing suffering, more so as the other products of the virus are generated, such as gas. That would cause the host to begin bloating and literally tearing from the inside out. We'll touch on this phenomena as we go later on in the video. The virus would of course be expelled from the host as an aerosol. This would open up the opportunity for new infection, whether it's being expelled as something being exhaled in respiratory drops, or possibly from individuals rupturing and causing an explosion of virus-filled gas. That's going to work for creatures that breathe, and certainly for creatures that have the, epithelial cells we're talking about, but not so much for plants, fungi, and bacteria. We could bridge this gap by, again, going back to the idea of a virus super-related viruses, bacteriophages of bacteria, mosaic viruses of plants, and so on. And as each of these is, slowly cooked from the inside out and eventually explodes in a gaseous cloud, it would spread the virus in a rather disgusting manner. This way would lead to all organisms acting as both host and vector for infection, at least on land. But then we need to look at it in aqueous environments, for instance, and this is actually more so helpful than anything. If it is able to survive in, let's say, the oceans, which are quite salty, the mountains, which are often quite arid and cold, deserts, which are, dry and hot, and even open to the sun for a long period of time like the norovirus can, it opens up the opportunity for spread, reinfection, and sustained expansion, particularly though, again, in aqueous environments where the virus, due to the way it gets spread, would be spread quite far in the water, and then currents would carry it around. But this, of course, does bring us to the issue of spread. Remember, the virus should be able to get past even Astartes, respirators, filters, and practically melt the inside of a black ship. That is, the products are nasty. The virus must be able to survive, at least for a time, more so when the cells break down producing this while the virus is being produced. One obvious possibility is that the virus is really tiny and therefore able to get through the filters, but that seems unlikely. So we now need to look at what it's doing and to some extent how, particularly with such a wide strike range of targets. The obvious answer is actually going to be death. That is the whole point of Exterminatus, but it's also the mechanism by which the virus can spread more effectively. The simple answer is, it's as to how you die. That is, the cells are hijacked by the virus. This leads to the cell's DNA not being copied, the proteins in their cells cannot be made, and the virus needs are being prioritized. It's like being a very selfish boyfriend or girlfriend, but smaller, less vitriolic, and parasitic. And this, is packaging generally made from the cell's own membrane, which is a problem. It quite literally starts to put holes in the membrane to start with. That is harmful, but it may lead to lysis, or it may not lead to lysis immediately. If it doesn't, eventually the cell either gets so damaged that the cell undergoes apoptosis, which is a fairly obvious adverse event, because the cell breaks apart on its own, or possibly due to the immune system picking up on it. The other option is the cell is full of virus and they want out. Just like a chest buster, they trigger cell death and burst out like a, viral wave of death seeking new host cells. This process will cascade so long as the immune system cannot get on top of the infection. In fact, it's possible that the immune cells, given the way they, undergo population explosion during infection, might well be a target for infection. It's a good candidate at first for this reason, as it will also suppress the immune system, ensuring the Life Eater virus can work hard and well, while also giving it a whole bunch of new host cells that, will just keep on populating as long as they can and growing quickly to try and get on top of it. The body would surely, but slowly, be destroyed this way, as more cells are lost and cannot be replaced. That is, tissue is permanently damaged. This also leads us in one way that the Life Eater virus can get around things like filters. As more tissue is damaged, the host loses the ability to survive. This can be due to shock from fluid loss, where the body cannot hold the water in place. The cells just cannot make required materials such as proteins. The outright creation of wounds and possibly less likely festering slow death from infection, and arguably the eventual lysis of the whole human where it ruptures, like a water balloon that's been overfilled. One thing that it does do, and it's increasingly likely to be this last possible pathway, is that the inside of the body is turned to acid. That would, in part, reduce the infection risk, but it would also cause further harm through non-infected tissues being quite literally melted. If the acid, virus, and suffering does not kill you, the possible cardiac rupture caused by the ever-increasing pain will. At least you're going to hope it happens that way, because if you don't die from cardiac rupture, you're in for suffering. A lot of suffering. At the same time as the body is slowly destroyed and there is, well, the hope for immediate death and the sweet relief that will be, there are some fairly major byproducts made, byproducts that could explain how the virus gets through filters, for example. We have an idea about how the life eater virus might work, and particularly in terms of how it infects hosts, but we don't necessarily know about what it's making, and we do have some idea what it's supposedly making, the biggest of course being methane, but we could just easily say natural gas in wider terms, and it would honestly have the same effect, but methane is possibly a key to this. The first thing we need to note is that the life eater virus is meant to make an acid. This is either very fortuitous on the part of Games Workshop, or someone actually gave this some thought. But acetic acid, or in very simple terms, pure vinegar, can lead to the creation of methane. Also, pure acetic acid is very nasty, which could theoretically melt through filters and the inside of a black ship or any other vessel for that matter. To get methane, and to get methane from acetic acid, we do need let's say an environment where there is little to no oxygen, as oxygen will hinder, and particularly in larger concentrations outright prevent, the generation of methane from acetic acid. What happens is you have carbon dioxide and free hydrogens. The free hydrogens will come from the acid, and these bind together. Now, this will make water and methane. That's one possible way to do it, and when you have acetic acid, we get another pathway again. This produces another methane and more CO2, but remembering, acetic acid is, well, an acid, and acids like to donate their hydrogens. Therefore, you could have the acetic acid effectively dumping its hydrogen into CO2, causing the release of O2, which will be useful for the combustion later on, and eventually leading to the creation of more methane. Now, this is very much hypothetical and theory crafting, but it does mean the more you break down proteins and free hydrogen from the protein chains or polypeptides, the more hydrogens are available, and this can enter the equation, along with sugars, amino acids, and anything else. Along with the acetic acid, you get more and more methane being produced. More so when you break these down and release acetate, and the acetate can then become acetic acid in a hydrogen-rich environment, or inversely, acetic acid can become acetate, much like we've described. That does lead us to the question of how much methane can we get, and, well, we can use the average human as a simple example. The average male is approximately 160 pounds or 72 kilograms. Of this, 15% should be fat and 36% muscle. That's what we'll look at as far as what can be used to create methane. With a total of 51% of 72 kilograms, we get 37 kilograms of methane produced, or at least methane-producing material, per male on average. There are 4.03 billion males on Earth, and 4.03 by 37 gives us a really long number you can see here. At standard density, this is another really big number, liters of methane. For women, the numbers differ a little. At 140 pounds or 63 kilograms, we get 25% fat and 32% muscle. That leads to 57% of the 63 kilograms or 36 kilograms of methane-producing material per female on average. As per the method for males, we have 3.99 billion females multiplied by the average of 36 kilograms, and we get a massive number of methane. At standard density, we get another big number in liters of methane. The combination of male and female methane produced is equal to 6.514 by 10 to the 14th power joules of heat when you burn it. That might sound like an odd thing, but when you actually take that number and you apply it to something like, say, water, it's enough to raise the temperature of all water on Earth by many, many degrees Celsius. As we calculated, it's 1.98 by 10 to the 31st power degrees Celsius. That is effectively 1.99 followed by 31 zeros before you get to a decimal place. That's a huge temperature. Of course, this does assume that we're just talking about water, which of course isn't the case, but if it's not the heat that will kill everybody on the planet, it'll be the lack of oxygen from all this combustion. To bring all this together, we have both a simple problem. The life eater virus is too broad in nature. If it just targeted humans, it would actually be more than enough. It does not need to target everything, but that is assuming population density on par with Earth. A reach on many planets, except a hive world, wherein this would actually be a gross understatement of the population and you have absolutely no concerns. But it also means you don't necessarily need a universal virus, as fire will cleanse the heretic, Xenos, mutant, and fairy just as surely as the virus will. So Exterminatus may not happen. It should. We have an intractable case of the fairies, man-buns, and vegans, but for now, we don't have the means of committing the Emperor's will by executing Exterminatus on these mutants, heretics, and Xenos. Thank you for watching this video. If you found it interesting, consider liking, sharing, and subscribing. Please do post any comments, questions, or suggestions you have below.